Welcome to the MGM course, and today we will see some variants of GAN and how engineering is done for various applications of GAN. These are sheer engineering. The maths part we already covered, so the main idea remains the same, but it's just that with various applications you can change a little bit. So this will be the focus of my talk. So before we go there, since GAN as such is used mostly for images and also videos, so it's good to know a little bit about problems we have in the computer vision. Okay, so we can broadly divide computer vision problems into two parts: low-level vision and high-level vision. Okay, so in low-level, we refer to the initial processing steps that could be used in visual perception, where the goal is to extract basic features and information from the raw data. So in the low-level problems, you are only looking at feature extraction. Okay, it may not make sense until there unless you use it for high-level task. So these problems are foundational in both human vision and computer vision systems, serving as a building block for complex higher-level visual tasks that we will see, such as object recognition, scene understanding, semantic segmentation. So what is interesting is that if you go for the classical computer vision, there were many hand-crafted filters, and for almost various tasks you had different filters, hand-crafted filters. And with deep learning, CNN, and GAN, which is what we will see in this course, generative modeling, many of these things could be just done with the same model with slight tweaks. So that's why modern deep learning has changed almost all the fields, including computer vision. So it's not like for last 10 years. Okay, so most of the ideas are now features are extracted automatically, okay, by CNN. You don't have to go for handcrafted things. So low-level vision tasks focus on interpreting the basic elements of the visual data. Okay, so let us see with some examples. So let us say we have edge detection. So here we are given an image and we are supposed to find the edges here of this person. Okay, so this could be the output given the input. Okay, now this is a low-level task, so we will see how these things could be used in downstream task. So we can define edge detection involves identifying boundaries between different regions in an image. Okay, based on discontinuities. It could be based on discontinuities in the intensity of the pixel and so on, and based on that you can find the edges in the image. Okay, so this is edge detection. In general, you can talk about very generic sense image enhancement. So for instance, in this case, you can see the first image is blurry and you may want to make it sharp. Okay, so this is a very generic term here. So image enhancement. Now it could be many things, right? Contrast adjustment, noise reduction, sharpening, and all this. Okay. Now more specifically, if I go rather than saying in image enhancement, I can say let us do white balancing. So the room is a bit dark in the picture, can we make it brighter? Okay. Image sharpening, let's say. So this doesn't look sharp and we make it sharp. Vertical straightening. So this doesn't look vertical here, but then you can do some vertical alignment so that it looks better. Lawn replacement. I want to change this to this lawn. Okay. Other things remain the same. Okay. So all these are now done very well with GAN or like any other conditional approach. Textures. So images, some images have textures, and you may want to identify the texture and you may want to generate the texture. Okay, so again generative modeling could be used. So there are various types of textures, obviously, so you may identify them into various types. And again, if you go with the old idea of computer vision, then you may have different handcrafted filters for different specific type of textures. So someone may write paper for stochastic type of texture, someone may write it for filters for regular texture and so on. But with deep learning, we most of the things are now generalized. We see this as a pixel with certain pattern that we want to learn as a distribution we want to learn the distribution to produce this. Okay, it doesn't matter what shape or regularity is there in the image. We don't care. Motion detection could be another topic where there are some spy cams and you may want to detect some intruder or something. So these are pretty evident problems. Optical flow problem is when given a sequence of image, you want to say what is the motion in the image. Okay, so in this case you can see some cars moving. So someone might have given you let's say some couple of images, and based on that you have to say that okay, this is the direction of the cars. Okay, they are flowing through this direction. Okay, so this is the optical flow problem. And the classic image segmentation problem, where given an image you want to segment and say which basically just identify separate objects. Okay, and that's called segment. So in this case you made a box around car and there is a segment around car. So this part is a car, again there is a car here, there is a person here. So you are basically segmenting different objects in the image. So this is the segmentation problem. If you go to high level vision problems, they involve interpretation, understanding, reasoning about the scenes, and so it's beyond mere detection or feature extraction. Here we also want to conclude on the image. Okay, so that will be higher level. So the higher level could be the recognition problem, where given a set of objects, I want to recognize which objects are there. Okay, so in this case, like it's a cycle and a building and so on. Okay, so this is object recognition problem. Scene understanding. So there may be multiple objects in an image, but then can you conclude in a broader sense what that scene is about? So in this case, there are many segmentations and all this, and you may have done the identification of the objects, but then can you conclude about something, right? So in this case, it looks like a image of a bedroom. Okay, so then it's a part of scene understanding. And then localization problem. You identify the objects, but then you also locate where they are in the image. Image captioning problem. Given an image, can you generate the captions in the image? Okay, so in this case, there is an image, and then you have to comment on that man in black shirt is playing guitar. Okay, and here you have to understand what is going on in the image. Construction worker in orange safety vest is working on road. Okay, so this is called captioning problem. Given an image, generate a caption. But what we will see also is other way, right? From a caption, we will generate image. So that will be text to image generation problem. Okay. And now recently you have seen OpenAI Sora. So if you write a text, it even generates a video now. So the whole entertainment industry, we don't know how it's going to be. Films may be produced by next year purely by generative AI. So things are happening very fast. Okay, by the time we finish this course, it will be outdated by almost a year. Okay, visual question answering. So it is like image is given, and then you are supposed to answer a question based on after looking at the image. So there are like two multiple choice question. In this case, is two choices are given. So you have to say like who is wearing the glasses in the first one. Then you identify it's the man wearing the glass, and here in this case the woman is wearing the glass. In this case, where is the child sitting? So you can say where is sitting. So on fridge, and here in the arms. Is the umbrella upside down? So you can say here it's yes, here it's no. For us it looks easy, but for computer these things are not that easy. So this is called visual question answering. So if you want to do non-visual, then obviously you can look at our paper. So we did it for maths problem, maths and science problem before ChatGPT. So it could solve up to 12th class problems. So it was that was not visual, right? So you write a question that is text, and the answer comes in text. But this is visual question answering. 3D reconstruction. This is a problem where you have seen the object from multiple views, So for this same object, I have 4 or 5 pictures, let's say. It depends, okay. And then based on that, can you construct the 3D model of the image? Okay. So this is called 3D reconstruction problem. Here also we have a couple of papers, like I listed one paper here. The recent ones are NERF. So NERF is becoming has become state of the art now. So this is called 3D reconstruction problem. Then we have image in painting problem, where an image is given and then some portion of the image is not there. So can you fill that? Can you in paint? Okay? So can you complete that part? So this part is not there. Then this was the original image. So this is the original image, and this is the masked out image. And you build some model, whatever model you have. Mostly it's like deep learning based model now. So someone will give you this, and you have to predict this. Okay, this is your input, and this is your level, which is so it should produce the completed image. Okay, this is called in painting. Okay, here also we have some papers. So I'm also doing some marketing. So one of the question is like, is your model good only for this very regular patches that is missing from the image, or it will also work for irregular patches? Or what if I randomly remove some pixels from the image, right? So these are the questions you have in painting problem. So basically the picture may be distorted in many ways, many irregular ways also. And can your model recover the image? So the idea that we propose is a zero shot learning. So that's interesting. So another is occlusion detection. So sometimes in a picture there may be some person in front, but then you are also interested to know what is hidden behind the person. Okay. So basically here we say that some of the objects are occluded by some objects. Okay. So is your model good enough to find also the hidden objects? Okay. This is also part of object detection. So you may kind of say both are like part of, but then separately we can say can I find the occluded object as well? Okay. So okay, so now we saw there are quite a few image problem, and this will be some reference for us in today's class and also in future classes. Mostly we will deal with images at least for a couple of classes. Now we come back to GAN, generative adversarial network. This is the main generative model we have seen so far. So some of the issues that we may face with GAN. The first, we recall quickly what was GAN. So there is a discriminator, obviously, that learns to classify between real and generated images, and then there is a generator that tries to generate some image and tries to learn the real distribution. So if you go quickly to the scores or the loss, then the loss for the generator is given by average of the discriminator score that was given to the outputs that was produced by the generator. So that's what y hat means. Y hat contains the probability of the generated images, and this is given by the discriminator. The generator produces some output, and discriminator gives a score on that. So that is what is the score of the generator. And obviously, if the generator is bad in initially producing good outputs, the score is bad, and this score is used during training. And we tell the generator that go back and improve your weights because the loss is very bad. And generator does this. It takes the score of or 1 minus y generated here, and then also it tries to learn to predict. It is also learning to predict correctly the real data. So it's a competition going on. So it is also trying to learn discriminator. Discriminator is not trained already. Okay, so it's both is happening at the same time, and this also brings in a bit of difficulty in training GAN because of all this. Because it may happen that one guy may just run away because it's a min-max problem. So it may happen that one guy just dominates and other cannot really do anything, okay, in that sense. So we will see that, okay, shortly. So what I mean by that. So what are the convergence failures in GAN? So discriminator dominates, one case. So it's like one guy is pulling like this, another is pulling like this. One guy dominates, then the other guy is not learning anything, gave up. It can happen other way also. So these type of problems are sensitive. It's a min-max problems are like that. So this could be the case when you are training generative adversarial networks. Then if you plot the scores, then those score values, this could be one scenario where the discriminator dominates. So according to figure, if you see the red one, if you cannot or you may not be able to see, so red one is the discriminator curve. And remember, the maximum score that discriminator can get is 1, okay, because it's a classifier. So so it's, you see very quickly within 10 epochs it reached a score of 1, okay, and generator is here already kind of but looking at this, you may see that what is wrong, right? Things may look perfect, right? Because the generator got to 0 and discriminator is already at 1. So it means that discriminator is predicting all the images that is coming. A discriminator is predicting either from the real or from the generator. Discriminator is saying that it's all real. Okay, so that could be a very good scenario, right? But if it happens so quickly, then there is a problem. Okay, in these cases, there is something bad happening. If you see this so early, okay, usually the plots will be like this. Okay, slowly, gradually. If someone dominates very quickly, then something bad has happened with the generator. Generator might have learned a way to produce an image which is kind of always real. Okay, and there is no, so generator did not learn basically the to produce different type of images and so on. So in this case, generator score approaches 0, does not recover. In this case, discriminator classifier most of the images correctly. In turn, generator cannot produce any image that can fool the discriminator. But idea was generator should produce images that fools the discriminator for a longer time. So remedy when discriminator dominates. So what would you do in these cases? Let's go through this quickly because I have other things. So if the score does not recover from this, then it's better to stop training first thing. If this happens, then try balancing the performance of the generator. So what will you do? Impairing the discriminator by randomly giving false labels to real images. That's called one-sided level flipping. Impairing the discriminator by adding dropout layers. You may add some dropouts to make it more robust. We will see dropout is interesting. It makes neural networks more robust. We will see this a little bit more. Improving generator's ability to create more features. So it could be that the generator itself was very bad, that the architecture of the generator, the neural network that he used, that itself was not enough. Okay, it was enough to produce something that looks real, but it was not enough to kind of keep learning the diverse set of data sets. So it may happen that your generator is underpowered. Okay, so you may increase the number of filters, make it more powerful, and discriminator seems powerful, so you may want to decrease the number of conv layers or filters, whatever you have it there. Okay, so these are like from practice. Okay, these are suggestions you are given from practice. Like, we are not trying to explicitly prove these things. Another case is when generator dominates. So in this case, the generator is getting a score of 1 and discriminator drop down very quickly. Okay, any graph that happens like this very quickly, you have these jumps, then this is a sign of something is not, I mean, one way is like you just let the generator produce the images and you will see that those images are not diverse. Again, you do similar things. Here you have to play around again. So in this case, maybe the discriminator requires more number of filters in this case. and you may need to impair the generator by adding some dropout layers and so on, or by reducing the number of filters. So these are some general strategies given to you. You may try this because it's also dependent on the architecture, what type of architecture you're using, ResNet or UNet or all those things. So mode collapse is an issue in GAN. In the assignment that I gave you, it is likely that mode collapse might be happening, although I have to see exactly for that data set. But because the architecture that you implemented in assignment was a very basic one, you did not even use convolutions. It was a basic ANN. So those are not very good. So this is called mode collapse. The mode collapse is a problem where the generator produces only similar type of data. Okay, so in this case you can see, I believe it's flowers. So it's producing many flowers and then some other type many times. Now if you see the score plot of this, the scores will suggest that there is not much wrong, because generator is producing good quality images. Let's say it's still flower. Let us assume that this is good quality, and discriminator is saying that okay, it is a good one. I think it's a good one. But what is missing from here is the diversity, because generator was supposed to produce diverse set of images. So generator is again fooling here. Okay, generator learned very nicely to take a random vector and produce same type of image. So this is also called fooling. Generator is just learn 2 or 3 mappings from random vector to 2 or 3 classes. That's it. Yeah, so the remedy for mode collapse is very similar to what we discussed, because this is not a separate issue what I'm saying. Okay, this could be this belongs to one of those generator dominates and so on. So again you may do the similar thing, like make the generator more powerful, because mode collapse is happening perhaps because generator is kind of not very powerful enough to learn too many interesting features. Okay, the dimensions are so small that it just prefers to learn this, because at the end of the day generator is trying to kind of make its score better, and given the resources, the generator given the limited resources, in this case is like limited number of weights and conf layer, then the best thing it can do is produce multiple copies. Okay, so again you may impair the discriminator again by giving some false labels to some real images when you're training. Okay, so these are some another issue that we may face is from the optimization point of view, and this is the GAN algorithm. And here we have, in fact, at the heart of GAN algorithm is this optimization problem. Okay, maximize the discriminator and minimize the generator. So minimize D, mean of D, and max of D and mean of G. Now one of the issues could come from how you are doing that, how you are solving the optimization problem itself. The optimizer may be there to blame. So there are 2 things, architecture and optimizer. Okay, so previously what we were doing is like, let us increase the power of the generator, let us decrease the power of the discriminator. That's like architecture issue. But at the top level it may be that the optimizer itself is not a good one. My G and D networks are very nice, but the way they are going to minimize and maximize itself is not happening correctly. So one line of research goes in this area. Okay, you think about nice optimization methods. So in the traditional, this is Goodfellow GAN taken from the original GAN paper, and they were using gradient descent. So as you know, gradient descent is a very basic method, and gradient descent as such is good for min problem, but when you go to min max, it suffers from symmetry breaking and things like that. So for example, fxy is x times y. Try to do min of x, max of y, and you will see the issues with the gradient descent. Okay, so in general it's not a good idea to use SGD. So one of the things we can see is non-SGD is the blue one. So in papers it has been demonstrated, also in some of the papers we also wrote, but this is CGD paper. So it is their method, and you see Adam is also first order method. Adam is like slightly more sophisticated in gradient descent. It does momentum and some variance corrections. So they are comparing with Adam, and ACGD is the blue one. So higher is better. Inception score, if you recall, Inception score is the score given for CFAR 10 data set. You can also do it for 100. So this means 10 classes, so 10 is the best. Okay, the higher is better. So so 7 point something, okay, is achieved by CGD. So this is an optimizer thing. Okay, all the methods are compared on the same architecture, but it's because of the optimizer you are getting better results compared to first order method ADAM or some other like OGAN, orthogonal GAN, and so on. So optimizer can also play a role, and then many researchers focus on this type of work as well. So optimizer as such, this is taught in optimizer course usually. So I will not go in detail of these things, but just for your information, there are many type of optimizer. These are first order method: SGD, ADAM, RMS prop, ADA grad, ADA delta. But here consensus optimization is a second order method. So this does better than the first order method. You can also do something like spectral normalization. That seems to help quite a lot. In spectral normalization, what you do is that you normalize the weights of the discriminator by spectral norm of the weight matrix. So basically, spectral norm here would be like you take a SVD and divide by the largest singular vector. Okay, so this is a simple idea. You may look at the paper for detail, but it's a very simple idea, and that helps quite a lot. Okay, so spectral normalization could be done. Of course, this is not an optimizer. This is like normalization scheme. Then obviously WGAN itself comes with GP, and we have already covered that. This is what I showed you in the figure, competitive gradient descent. So that was like doing better than ADAM. We also did some work along these lines. We got these things published. Like this was also quasi second order methods. This is another paper. So if you see this loss, then this is a loss from big GAN. Big GAN is, you can see, almost state of the art. There is giga GAN, big GAN. So they produce images as good as diffusion models. So if you see big GAN, obviously everything is the same, right? There is this log loss, discriminator, generator, and so on. But what you see here is that the weights are orthogonalized. Okay, so the way we wrote in the paper is we use some manifold type approach where we so what big GAN is saying is that you do the min max of the GAN, but make sure that the weights are orthonormal. Okay, so that helps. That's what the big GAN paper said. So that means that this is not just a plain min max problem. It is not unconstrained now. If you are looking at the weights of generator and discriminator to be orthonormalized, then you have a further constraint that min max, but weights are orthonormal. So there is this space. Okay, space of orthonormal matrices called Stiefel manifold. Okay, so one could use that, and some ideas we can borrow from there and develop a solver for these cases. Okay, so as I said, these things are better discussed in optimizer courses. So now I will move to the other part, I guess. So there are many variants of GAN. In fact, there is a list someone made on GitHub. There are like more than 50 variants of GAN. But obviously not all are like very, you may say that minor changes here and there. But it is worth looking into some ideas that are very interesting, and you may kind of use it actually. So the way we will see some of these ideas is in a sense that we can use it in research. Okay, and so that's why I selected some of them which could be interesting. So I want to cover progressive GAN and pix-to-pix GAN. At least I will go until pix-to-pix, but perhaps I may not be able to cover that completely. And style GAN also I will cover maybe in the next class for a couple of minutes, and that should be done. And others I will just leave as an application. I will show you what they are doing, and then we will move to other set of generative models, and we will go back to maths again. So progressive GAN idea is these things are all engineering ideas. Okay, so for the last 2-3 classes we are mostly doing these things. So so it emphasizes the innovative approach of training GAN. Okay, it begins with a low resolution basis and gradually adds layer to capture fine details. So this is the main idea. Okay, so can you do things like this? You may need this. That's what I'm saying. gradually add layers to capture finite details of interest. So this is something interesting they found. Okay, it accelerates the training process, enhances stability through training, enables production of high quality images. So basically you may use this for super resolution again. Okay, so it achieves a record inception score of 8.80. So that is pretty high. Remember 10 was the highest, it's getting very close. So this was significant in their paper. That's it, and they used on celeb data. So celeb data set is a data set of celebrity faces. Okay, so they basically use that. So this is the idea of progressive GAN. So let us see what is happening here. This is the generator architecture. This is the discriminator architecture. So as we know, generator takes random variable which is denoted by latent. So it goes through some conv layers. So by now we know what is conv. So in this case it's like 4x4 convolution layer. And depending on color and images, we will have multiple of these channels to scan. So there will be some 4x4 blocks, and then generator will produce some image which initially will look not very nice, or in this case it's like, let us say, even if it learns in this case using 4x4, it can only do this much. Okay, because the conv layers are not that powerful. And then this goes to discriminator, and discriminator will judge based on these outcomes. Okay, so this is what you may do typically when you have some set of conv layers like this, and then finally some image output, and then it goes to discriminator. Discriminator gives a score whether it was real or fake, and keep doing that and until you train the generator, and later you can start producing images. What they're saying is, like, let us do it in a progressive way, in the sense that you increase the conv layer sizes. So you went from 4x4, but progressively. By progressively means that you do it after some epochs. Okay, some epochs keep the original one. Some epochs you added some additional conv layers, and then it produces image like that, and then it goes to the discriminator. Discriminator again is learning to predict on these. Okay, and basically the idea is that you keep doing this progressive training. Okay, so as you can see here, now progressively you started from 4x4, and you are increasing this these conv layer sizes. Okay, basically you are upscaling. Okay, and you are scaling up to 1024, and then the discriminator picks up from there 1024, and then it goes back to 4x4. Okay, so the progressive GAN idea is to add bigger and bigger conv blocks, and we should do it progressively, not like, so you may say, what if I go directly here? No, that's not what they suggest. They suggest that you go it step by step. Okay, so that's what it's saying. As the training advances, we incrementally add layers to G and D, thus increasing the spatial resolution of the generated images. All existing layers remain trainable throughout the process. So here, for n by n is the conv layer operating on n by n spatial resolution, and it is growing until 1024. But there is a little bit more here. The little bit more is this guy. It was not just the blocks that you added were bigger, like 2 times from here to here. What they did is this this thing as well. You can see this is a rest block. Okay, the residual block. But this residual block is done in a way that they have this 1 minus alpha and alpha. So what they're saying is, like, let us do a linear combination. So this output that you got after 16 by 16, let us say, is X, and this output that you got after 32 by 32 application is Y. Then the final output that they get, they call it plus here. So final output they will get is Z equals I think it's 0. Yeah. So 1 minus alpha X plus, it's a convex combination. Okay, and this alpha is also varied. So if you keep alpha to be 0, then this would mean that it will use just this initial block. Okay, and if alpha is 1, then this won't be taken here. It will indeed pass through completely through this upsampled output. Okay, so this is also part of the progressive training that they suggest. It says that let it train not just I added the additional block, but I'm also saying that the effect of the additional block initially would be very small, but gradually I will increase alpha from 0 to 1. So 0 would mean that I'm in the old regime like this guy, and 1 would mean that I'm taking the effect of these upsampled output which is going through 32 by 32. Okay, so this is also part of progressive training, and they said that this helps their case. Okay, so that's and apart from this, the usual initialization that we learned in the previous classes, those tricks are used here. So first thing is weight normalization, and we have seen JVS initialization. We could not complete the proof, but at least we know what it was. And later we also saw her initialization. So they are using her initialization here. So basically weight is normalized in a way that the variance of the weight is half of number of layer of the number of nodes in the layer or the current lth layer, and then the variance of the WL should be 2 divided by NL. So the weights should be initialized in a way. Okay, so this was Hurst initialization, right? So this is how you initialize the weights initially. Okay, all so this is layer wise initialization, right? Because there is a dependence on NL. So N1 will decide different type of weight normalization compared to NL plus 1. Okay, but you have to do it at the first step itself. That's it. Because when you start training, these weights could be initialized in many ways. It could be 0, it could be random. But what we saw in the previous classes is that there is an effect how you initialize. So Progressive GAN also found this interesting, that if they initialize like this, it helps. This is weight initialization or normalization. And another thing they did is feature vector normalization. In feature vector, you basically normalize the features. So these are your features A, okay, and then so there are weights and there are features, right? So you take a linear combination of like this, right? So let us say the output here. So these are the weights, and these are your features at the some layer, let's say AN, and these are like W1, W2, W3 to get an output here. So you may also normalize the features by dividing by the sum of the squares of these features. So there are two things as a weight normalization. These are engineering things, but it's useful. Okay, you may not be able to ignore it. You may do very good maths, but you may if you ignore these things, maybe your method may not give the best results. So Progressive GAN is that much. Okay, you may try this even in your existing assignments. You may change to conv layer, and it's very easy to test. Okay, just add these things, so you can play with these things. Okay, now let me go to pix to pix, but as I said, pix to pix, I may not be able to completely deal with that, but going towards pix to pix, we will recall few things, and along the way we will do in-painting using GAN, but we will not go to pix to pix. Pix to pix is a generic idea, as the name suggests. You may think of any image processing as translation problem. Pix to pix, it could be anything, like in-painting, okay, sharpening, segmentation. So it's a translation problem, right? Given an image, you want to do something to get an output. So they use GAN for that, but we let us before going there, because some of the ideas used there, it will be useful if we know something before going there. So that's my plan. They propose a general purpose solution to image-to-image translation problem. Image-to-image translation problem. So thanks to GAN, this is possible to have generic ideas. Okay. So these networks not only learn the mapping from input to output, but also learn a loss function to train this mapping. So all these details we will see. So, but before going there, there are a few things we should recall. Encoders, denoising autoencoders, some historical context will be useful. Maybe you are aware until encoder, maybe, I don't know. Denoising autoencoder is an interesting idea, and they are all related, and then context encoder. So let us see these characters in this story. So we'll come to pix a bit later. Let us explore few things on the way, learn few things on the way. First thing is PCA. I'm not going to do this PCA precisely right now. Just for record, I put this in the slide. So basically, encoder decoder, the most basic form could be seen as PCA. Okay, principal component analysis that you already know by now. So in principal component analysis, you basically do this decomposition like this, where y you could write this as t times p transpose. So it's a matrix factorization of y, and then some error that you get. Okay, and p here the columns of p are the eigenvectors of the covariance matrix of y. Okay, so it depends how many of these eigenvector you want to extract. Let us say f largest I want to extract, depending on how much it's a hyperparameter, so you have to decide how many of these eigenvector you want to extract. And then you reconstruct you may reconstruct it by doing this. Earlier you did PT transpose, and then you may reconstruct the data back by y transpose is t p transpose. Okay, so and then you may want to compare, right, the reconstructed one. So then y prime you got it from y, and then you may want to see that the constructed one has a minimum norm. Okay, so PCA is a kind of a compression technique where I may compress the data and then want to decompress it back and check whether the decompressed data is good or not. Okay, so so this is PCA. I'm going fast but because I know you know these things. So then an extension of PCA is nonlinear PCA, and so you could do PCA in a nonlinear way, and the trick could be to use neural networks. Okay, so nonlinear PCA is a novel technique for multivariate data analysis, similar to the well-known method of principal component analysis, which is an extension, nonlinear extension of PCA. And it adds in, as usual, the same thing that goes with the usual PCA. It helps in dimensionality reduction, visualization, because if the data is small dimensional, I can visualize that. For exploratory data analysis, right. So let us look into generic variant of PCA. So we are looking for a map that takes the input vector g, I mean y, that passes through some nonlinear function g, and it produces an output t. Now g could be seen as a nonlinear function where each of the component of the g could be some nonlinear map. Okay, so t itself is a vector. So what we are trying to say is like this: we have a y, and it goes through g, and what we get is t. Now t itself is a vector. So each component of the t, I may see this as t1 is coming from multiple components. In this case, I can see this as f components. So it may be coming from these, and again the second component may be coming from these, third component may be coming from this. So with this view, I can see each of the entry of t coming from some nonlinear map. Okay, where it could be some combination of g1 to gf. So this is what I said. Ti could be seen as some function mapping some nonlinear function taking gi, which takes y and it produces ti. So, and we can also look at inverse transform to maybe recover the y. So inverse transform could be seen as a nonlinear map H, and H inverse transform itself may be seen as some m components. It does not have to be same as the f. Okay, we are not really looking for equal components here in this case. Okay, there could be variable, but y prime is our reconstructed image, and then we can look for the error, right? So error will be like how far is my reconstructed y from the original y. Okay, so this is nonlinear PCA. So we can draw this as a diagram. So this is our G map, and that acts on Y, and it produces a T, and then the inverse transform H takes the T and it produces some Y prime. Okay. So input was Y, it went through some nonlinear map G, I got some intermediate output T, and then I did a inverse transform to get Y prime. And it is nonlinear because this mapping is nonlinear. So G and G could be some nonlinear function. Okay. And what is the best nonlinear function? We all know is these are neural networks. Okay. It is proved. I will give you a reference. Why neural networks? Although I have already taught neural networks, but because of this result, approximation by superposition of a sigmoidal function. So this is just, so in this paper we demonstrate that finite linear combination of composition of fixed univariate functions and set of affine functions can uniformly approximate any continuous real valued function. That's why we are using neural network. Okay, I just thought that it's good to kind of say these things. So let In be n-dimensional unit cube, the space of continuous functions In. In this, so let us say the space of function is denoted by Cin, and this denotes the supremum, and f is one of those continuous function. Then the main goal of this paper is to investigate conditions under which the sums of the form are dense in the space of continuous functions. What is dense? What is a dense set? Okay, I have not taught to the to the UG guys. Again, there's a slight extension here. So dense, for example, rational numbers are dense in real. So basically, closure of if the closure becomes the full set, then it's dense. So A subset of B is dense in B if closure of A is B. So closure means what? Closure of a set means that I'm looking for the limit points. There were some limit points of A, were not in A, I will put it. So if I keep doing that, all the limit points of A that were not in A, I will put it, then I closed it. So rational number, you can do that, right? The rational numbers, you see, is it true that all irrational numbers are limit points of rationals? Right? What was the limit point? Like whenever we take a ball, then we always get something something intersecting from the set, right? Limit point does not have to be in the set, but that point is such that whenever I take a however small ball, it always intersects with some point, right? So this is for irrational number will be like that. Around irrational number, whenever I create a ball, a non-zero radius, it will always have many rational numbers. So any irrational number is a limit point of the rational number. So in the set of a rational number, I have to put all the irrational number because all are limit points. So the closure of the rational number will become rational number plus irrational number, which is real number, right? So Q is dense in R, real number. Okay, Q is dense in R. So that is what is being said here in a slightly maths-oriented way. What they are saying is that if you take any function from Cin, so what they are saying is like Cin. So this type of function, Gx type of function, which are like this, right? So these are spatial type of function, right? What you are doing here is like some yj transpose x plus theta j, and we all know what this means, right? This is exactly neural network, right? So this is basically what we have seen already. So this is nothing but a neural network. You did a linear combination, activation, and then one more linear combination. So what this is saying is that the functions that you get via neural networks are dense in the space of continuous functions, meaning they can arbitrarily approximate. They are close to any continuous function, arbitrarily close. Okay, so this is the result. So that's why we use neural network. That's why neural networks are so powerful. That's why it works in almost any scenario. Now it's being used in science, genetics, protein folding, you name it, to solve maths. There is some reason behind that. If someone is just saying it's nothing, you should be a bit careful because it is really powerful. Okay, maths also says that it's powerful. So so this is why we used neural network. Okay, so we did a little bit of a detour, but it's fine. So what we know is nothing but these guys are actually neural networks, and this is the reason why the all the revolutions that we see right now these days behind neural networks. So a nonlinear PCA is what he is trying to say now is I am trying to develop this nonlinear PCA like this, right? So in his paper, his whole time he's trying to say, because these are very old papers. Neural networks are just there, okay? So they were still trying, like many people were not really convinced that neural networks. So you had to cite things like, look, they are powerful, they can approximate any continuous function, and that is how you motivate your paper. And then you say, yeah, I propose a nonlinear PCA, and let me use G as a neural network because they are very expressive. Let me use H also as a neural network, which is very expressive. So in whole paper, it says like that. So if you see here, it's more or less same thing being said here. So I can skip this. So nonlinear PCA is like this. There is a encoder and there is a decoder. That's how we are going towards encoder decoder. From encoder decoder, we will go up to image in painting Y again. Okay, this is the thing. This is how we are going. So encoder network itself tells you quite a lot, right? So encoder is some neural network that took some input and then it produced some encoded values. In this case, it's T, right? And there are F of these encoded outputs. And these are nonlinear because if you say sigmoid itself is a nonlinear function, 1 divided by 1 plus e to the something, right? So the sigmoid itself is a nonlinear. So nonlinearity is definitely there. And these guys are nonlinear. Inverse transform is also nonlinear. So this could be your input and this could be your reconstructed input, this output, okay? And this could be used in many ways, also for images, right? You can already see how this idea could be used. For instance, you can compress an image, right? So someone wants you to build a compression of an image. You may use this as a compressor or and decompressor. You compress, you know how to compress an image, and you want to send it to your friend. You send it. Because this is very small, this is usually called bottleneck layer, okay? And this is kept small. There is a reason behind that. So this is small, so through internet you can send the zip file or whatever. That's exactly compression, right? And then you also have this network because you train these networks already. So you have a decompressor also ready. You decompress and then you get back the original image, okay? So very basic idea, just like PCA, compression, decompression. Here also we can do compression, decompression. So although I've written these things, not everything is super important for us. But as a slide, it makes these slides complete. But I don't have to read out everything. Okay. So that's it. Okay. So now, obviously, we don't want to see this as a separate process, right? We don't want to say, let me build the encoder first, then I will build the decoder first. We will do end-to-end training. In fact, this is one of the things also said in the paper that let us. So the term used, these are old paper, right? The term used is like, let us use these networks in series. Okay, so series is like one after the other. Okay, so this is what is done: encoder and followed by decoder. Okay. Same thing like PCA, right? You can say PCA, you did the projections, you had your low dimensional vectors, and then you can do transpose of the projection, and then you get back to the original space. Obviously, the output that you get here may not be exactly the same output because the bottleneck layer might have compressed a few interesting things, right? And this is still an open thing, right? For a given image, you don't really know what could be the good one, right? Good compression, right? So this usually remains a hyperparameter. Even when you do PCA also, if you don't know much about the data, you don't really know how many eigenvectors to take and project. You don't know. You might have taken less, you might have taken more, you could have compressed more. So these are, again, hyperparameter, right? So this is our encoder-decoder model. So combined network is trained so that the weights of the network G and H are optimized. Goal of the optimization is to reconstruct the output y prime to the input y. Training is considered complete when the error, sum of the squared error, is minimized. So this is our error, right? So obviously we will train this on a lot of training data. Okay. So in our case, the training data is just the input itself, and the level itself is the input itself. Okay. So So we will just compare the output produced here with the same y, this y, right? So and we may compare this with L2 loss. In this case, it's this loss. So difference is square of the sum of the square of the differences. Okay. And in those days, yeah, they may not have used gradient descent because they prefer to use conjugate gradient descent, which is another type of optimizer used for back propagation. But these days, conjugate gradient descent are not very interesting. Okay, especially in the stochastic setting. Okay, so this is encoder decoder. This is a nonlinear PCA. Now let us go to. So we know nonlinear PCA is encoder decoder basically. Now we can look into masked autoencoder. Now let us look into, this is just a slight variation of the encoder decoder. So what this says in the diagram is now your x is an input, okay? So x is your input. This x goes through some QD transform, and this transform is simple. This is saying that just remove some entries of the x, okay, randomly. There is no preference as such. How much you will remove, it's up to you, but you remove randomly. So this Q randomly identifies the index of x that's going to be removed, okay, and then that's why the name is masked, okay, and then there is a f theta that is trying to do the encoding. So here f theta is our encoder. So usually the encoder size is less. So this is encoded value is y, and then we have a decoder which is g theta prime. So g theta prime is trying to now take back y to the z. Okay, so this is our constructed. You may say this is our constructed image, and this is our input image, and then we have a loss function that will calculate the difference of x and z. Now again, loss, which type of loss we will choose, that's also we have to think. But this is kind of the idea, right? So you may say, why did I do the masking, right? Why? It is essentially encoder decoder because x goes in. So if I have to write this in the encoder decoder form, then f theta of x, and then g theta prime of f theta of x, and what I get is the z. So this is the encoder decoder. X went in, it got encoded, and then via g it got decoded. But there is an additional step here where I am doing some masking, random masking. Okay, so this is the idea of this. It's a very simple idea, and the main reason is that so this is the objective function here, which is now evident. You see, x hat came via d first, right? So basically, you come and create this x tilde, and this x tilde is taken by f theta, and then g theta prime acts on that, and then you compare with the x. So that's it, right? So that's what we want to say. Compare the input with the reconstructed output, right? Input. So the paper suggests that if you do this, it helps in the robustness of the decoder, okay, encoder and decoder both, because by changing by just removing some of this, you are making it more you are giving it slightly more challenge, okay, to even recover even after removing few of the data, okay. So basically it's a way to give some additional challenge. Obviously you should not remove too many of them as well. This also can be an hyperparameter. So this is the theme of this paper, okay. It is robust to partial destruction of the inputs. If I can train it that way, it's like to a child you may give a full book to read, but then might be sometimes you might remove some pages from the book and still want the child to kind of learn, fill in the blanks, few things, because it may happen that everything in the book is not necessarily unique. So this thing where you recover from some, not from the original input, but also from some slight distortion of the input, that makes it more interesting, okay, or more powerful network we get. In fact, this is also some of the themes that we will see also in diffusion models. In diffusion models, one of the ideas is that given a input vector x, you add some noise here, okay, and then you get some image, then you add another noise and make it completely noisy. By pure noise we mean some Gaussian, okay, and then you want to do it step by step denoise. So the noise that you added like this, and then you have to learn the process of denoising step by step. So this is in the similar theme. The masking that you see, it could be seen as some way of randomly putting a noise in your data, okay, hiding few things and letting the network learn this, okay, so then it will work harder, okay, and in that way it will become more robust, okay. So it's like more powerful training that we want to force, okay. So this is the denoising autoencoder. So in addition to input sample from trained data, a randomly corrupted version is produced. So everything I said, a gradient step is taken based on these selections, and useful feature representation for downstream tasks. Okay, so when they proposed this paper, one of the goal was feature representation. Okay, it's like when you do this masking, then the concepts that you are learning, even after some of the things are missing, you are learning more powerful features. So these ones, intermediate ones, we call it features, compressed, because when you do compression, then essentially you are focusing on the key ideas, right? So someone like said in the model that why don't you give me cheat sheets and everything, okay, we will solve, why should I memorize and things like that, right? But that was the step where I wanted you to go to the compression part, right? So I was forcing you to compress, just keep the important features, what you learned, right? So if I'm proving the KR dual form, what were the key ideas? That is exactly the part, because if the cheat sheets are given, you are not forced, right? The whole idea is to challenge you, right? So this is how we are challenging, right? Here the encoder is also doing the same thing. Comparison is a part of learning, okay? That's what. So this key idea will be they did not show that it could be used for inpainting. Now you can say that then it should work for inpainting, right? And in fact it can work. The only thing is like whether it will work better or not, because you can see this as an image, and then some proportion of the image are distorted, meaning the pixels values are gone or randomly changed to bad values. Then if you train these networks like this, maybe they will be robust to also do the inpainting task. So you may give an image and then maybe it will learn to predict, because it has learned during the training. That is what it did actually. Some part of the input were distorted and it learned how to produce that. And inpainting problem is the same thing. So after training, you just remove these guys and just input something to g theta, and g theta prime, because that is the. Now it will go to y also, sorry. So this is your corrupted data x hat. It goes through f theta. It produces y hat, and then it reconstructs the z. Okay. So during reconstruction, this could be your distorted image, because the network has learned to take distorted image even via this route. It was distorted, so it has learned to take distorted image and reconstruct the remaining part of the image. So this could be used as inpainting. But the paper mostly said that it is a powerful feature representation. So basically there is some important, interesting concepts being stored here that I may use this later, okay, for downstream task in some other type of problems. So, and this is also an interesting problem in itself. You will see papers publishing feature representation. There are surveys and so on. For our purpose, there is a link also to another type of generative model. It's called MADE, masked autoregressive models. So now what I will do is So there are a couple of concepts you have seen, right? So the first concept you have seen is this masking. Masking is a way to train more powerful, and dropout is also used sometimes. Okay. And another important concept we will learn is adversarial loss. How to use that? And adversarial loss we will borrow from GAN itself. So GAN will help us now in inpainting. So let us see how GAN is applied for inpainting problem. So this is the inpainting problem that I discussed in the beginning. That this is the distorted image someone gave you. Basically, this person is missing from the pixel, and then a human artist may make may do the inpainting like this. It filled like this. This is via L2 loss. So basically, you may use autoencoder, right? So you do compressor or decompression techniques also, just like denoising we did. So you may try similar ideas with L2 loss. And what this paper proposes is context encoder. So what he's saying is not just L2 loss. It's not just encoder decoder. You also use some ideas from GAN. Okay. So that's the context. So now let us go into a little bit of this. Now this is the model that they have. So given an image, distorted image, it goes through the encoder. So the usual encoder decoder we have seen, and then some neural networks are there and so on. So we don't have to bother about those. And then we go do the decoder, and then the decoder produce this missing part, and then we check, because we have the level also doing training. So we will check, was this reconstruction correct to what was in the image, and based on this you have a loss function. And if the reconstruction was not good, obviously you tune the weights, you do back propagation, you tune the weights, and you do this for multiple epochs. You change the patches sometimes here, sometimes here. Okay, so basically from the same image, you may have multiple variations, and then you can have multiple images as well. Obviously, since you are training robustly, then you may have multiple images with multiple of these corporate images, right? So this is just encoder decoder, right? So this is just encoder decoder. The story doesn't end here. That's the idea behind this. So how are generative models used here? The ideas that you see will here, these are intuitive ideas, but important ideas in the sense like similar ideas you may think. So I will give you one idea here, and I will also give you one more example from some other paper, and you'll see how to combine different losses with the adversarial loss and things like that. So it requires a little bit of practice. Okay, so how are generative models used here, right? So one possibility is, as I said, denoising autoencoder. But the problem with denoising autoencoder in the inpainting is that it does not respect the semantics. It does not respect the semantics in the sense that it will give us blurry. So this one. Okay. This is one exactly, because they are only using L2 loss. So you see the images produced by here. What L2 loss does is that it kind of predicts the mean of the pixels. Okay. It is a well-known problem with the L2 loss, that it predicts the mean of the pixel values, which minimizes the loss, but for our purpose it's not a good output. Okay. So this is a problem with the L2 loss. So you need more. Okay. So what if autoencoder plus GAN? Okay. And so play with the loss basically. Okay. So GAN and everything, we build the maths, everything, but for some applications we may have to play a little bit. Okay. So one thing is the L2 loss. L2 loss is this already. It's reconstruction loss, and here M stands for masking. Okay. So what this says is that for a given image X, you pass the corrupted image basically. So because during training you will remove some part, right? So this is your X, and if I apply 1 minus M hat, then this will remove this guy. Okay, so this is my corrupted image. Now this corrupted image goes to F, and this F obviously is kind of like trying to the F is the whole encoder decoder. Okay, so it's like it encoded, decoded everything. So after that it produced something which is not perfect for us. So let us say there is still some problem, but it did try to kind of reconstruct. And then you look at the part where it is, let me masking when you did, so the 1 minus m is when I remove, right? M is when I keep, right? Okay, so if I do m hat here, okay, it will be this part now. Okay, it will be this part here, and it will try to check with the so this error should be low. This is the difference, and there is a x minus also, right? Yeah, x minus of this, and then the only part that will be left will be this guy, because you did the m hat again, right? So it will just extract this part. A remaining generated one will be enforced by the adversarial loss. So this is what is happening here. It's checking the constructed part outside the patch. Okay, this loss. And what about the inner one? So so this is so they experimented with both L1 and L2 loss, and they did not find any significant difference. So L1, this is L2, right? You could have also used one norm. So L2 loss often prefers a blurry solution, okay, over highly accurate textures, because that's the problem of L2 loss. Okay, that's well documented problem with L2 loss. It produces blurry images as a reconstructed image. To elevate this problem, we added adversarial loss. So GAN has recently shown encouraging results, what we have seen. So yeah, let me write the loss itself directly. Yeah, let me see the loss. So this is the adversarial loss. So you see, in the adversarial loss, we have this guy, right? What is this guy, right? This is the one where we remove the patch, right? Yeah, we remove the patch. I minus m hat x, we remove the patch, and then we send it to the generator and to construct the original image, and then the discriminator will say okay, and the constructed image is good or not, and the discriminator is trained obviously on the correct image. Okay, so we are saying the generator, you construct the patch part. Okay, that's the generative part. So you construct that part, and the outer part that is also needs to be maintained is the other loss. Other loss saying is that make sure the outer part is matching, and this is making sure that the patch is constructed correctly. Okay, so and what is being corrected here, obviously the discriminator should flag it as a real distribution. Okay, so yeah, so what is happening, right? What is happening is the following. And there is no noise vector as such going to the generator. Generator is just taking the noise vector you can see is the one where the picture is corrupted. Okay, so basically this is the image, and this part is taken out. This is what generator trains on. Okay, so in place of noise, this type of data is going to the generator each time. Okay, and there is no conditional also here right now. Okay, no conditional. So just think of these corrupted data is the noise vector going in the generator. Generator will produce something. So generator produces something with some, I mean, it may not be perfect initially, obviously, and the discriminator has to say, and discriminator is training on the real data, so there is no patch. Okay, so discriminator sees the real data, and discriminator learns the distribution of the correct distribution of the data. So it knows more or less what type of generated data can be treated as a good one. So so this patch that is going to be generated by the generator will be decided by the discriminator whether this was correctly generated or not. Okay, so if this was yeah, so that's it. So that's what generator is doing here in this case. The patch region is being generated here. Okay, so one of the questions is, what if we use conditional GAN? Okay, how can we use conditional GAN in this case? Purely conditional GAN idea, what could be that, right? So how should we we use a conditional GAN in this case. Input, I can use some noise vector Z goes to the generator, and what is the condition that I want to put? Corrupted image. I guess it works, right? So corrupted image, and then it goes to the discriminator, and discriminator gets the uncorrupted image, and then it produces the that's it. It gives the score and so on, right? So let us say we train this conditional GAN, right? And what will happen then? We will, after training, we will remove everything, and what will happen next is that the GAN has learned that given a patch is removed, then it will try to kind of fill the patch. Okay, basically generate the patch part. Okay. So one could use conditional GAN like this, where the patch data is your condition. Okay. So during generation, then you will provide both. Okay, this is like class level. Okay, conditional generation. So whatever image you want to do the completion, you provide that as a condition, and obviously the random vector here, and it will try to inprint. Okay, so what could be the problem here, right? Why didn't they go with this purely conditional GAN approach? Because discriminator might learn this semantic boundary very quickly, and it will, no matter how good the generator does, just based on the boundary, it will say everything you are producing is fake. Okay, it will keep giving that score, because in the discriminator it will learn that this boundary is always there. With whatever generator is producing, it will quickly learn this boundary and always say, okay, no, there will be a slight mismatch always, right? But the discriminator will always discriminate based on that. No, your boundary is always not matching each time, because obviously it will not match with the exact one. So purely going for the discriminative approach is a bad idea, because we do want to allow a little bit of liberty of little bit of discontinuity on the boundary. Okay, this is exactly what the paper also suggests. They did try conditional actually. Okay, and in pix to pix, actually they will go for the conditional approach. So it will come back again, but with slight changes. And if you would have gone for the pure conditional approach, maybe you could do many type of image to image problem. So in this case, in image inpainting problem, there is a problem of well-defined semantics. Like this region is kind of semantically it's not like just the random pixels are missing, but there is a semantic that this patch, and there is a outside boundary that should remain intact. And another problem is another problem is, what is the another problem? If the generator is trained like this, if you implement it as a raw to produce this whole image that you are doing anyway, it might also change this part, the outside part, because it's a generative model, right? So it is allowed to kind of change this outside the patch region also. Okay, so there could have been a cat here outside. It might generate a new cat as well. But the L2 loss that we have, it is forcing that outside region should match exactly. Okay, so it is making sure that the outside region is not changed too much. If it is left on its own, generative model will generate, because generative model only GAN is more about a probability distribution. Okay, so it is learning a distribution as such, whereas L2 loss is forcing pixel wise. So L2 loss is making sure no, outside you are not supposed to touch. Okay, so that's why if you see the L2 loss, yeah, this one, right? This is outside one. Okay, this is the error for the outside. Okay, so these are like some of the intuitions that you develop while playing around with this. So then I can conclude with so these were some of the results from So this is something we want to cover, right? This is like the real image to image translation. So given an semantic thing, segmentations, I can generate a scene. Given this, I can generate the whole building. I can convert a black and white to color. Given a diagram like this, I can produce a picture like this. Given that it's a winter scene or the day scene, I can convert to the night scene. So it's not just in painting now. It is a more generic way to do image to image translation. Okay, so this is what we will see. So now there will be a slight change, and then we will get to this pix to pix. And very quickly, style GAN I will cover in the next class also. So there is this style GAN where you can copy the style from one picture to other. Okay, so if there is a source B, if it's source A, then what will you get? Okay, so this combined with this, what kind of image you can get? So can you mix the styles? This is called style GAN. There is something called Go Again, where again this is similar to pix to pix. You draw like this. You just say this should be waterfall, this should be some mountain or something like that, and then it generates image like that. Okay, so these are some applications of the demo of the Go Again by NVIDIA. Okay, and there is a GigaGAN, and this is as good as diffusion models now. This is like the state of the art. Okay, I won't go into GigaGAN. GigaGAN uses clip embedding. Okay, so I don't know if I will have time to use clip embedding immediately, and that is why the results are very good from text to image. Okay, because clip embeddings are also very good. So you can see very realistic kind of images being generated. This is text to image generation. Okay, and these are all super resolution things are. So this is why I'm saying even GAN is as good. Okay, so super resolution images are pretty good. Latent space embeddings could be done, which I will try to show you in an assignment. Okay, how you can do latent space embeddings. So basically, a modern mason is given there, and in the sunset, the same building, as you go from day to the sunset, how they vary, right? So same building, if you go from day to sunset, how there is a gradual variation, right? So how you can play with this latent space to do this small this gradual changes that you do, right? So these are all fun things. These are the state of the art for the GAN. Okay, so there is something called drag GAN, where given an image, you have two pointers you can put in. You can say this goes up, and make it smile, right? And then it generates an image like this. If there is a car and you put a 2 dot and say red one, I want to turn the car slightly on the way out, and then it changes the car. If there is a shot like this, you drag it, and then it makes a bigger shot. Okay, so these are all state-of-the-art applications of GAN in textile industry, in many things, right? We are not really applied guys, but you can see already so many applications of GAN. So this is more. This is kind of the state-of-the-art. There are many other applications, but let me stop here. I'm out of time. So this is kind of our wrap up of the thing. We will do pix to pix, which is a very simple thing, takes 10 minutes, and style GAN another 10 minutes, and then we will move to some other generative model. Maybe optimal transport, I will do it very quickly, and then we will move to VAE, and then we go to diffusion model. Diffusion model we will take about 6 classes, and then LLM maybe 3-4 classes. LLM is mostly engineering. I don't think LLM there is much to do, but I will introduce a bit. Okay then, so thanks. Yeah.